All right, section 6 from chapter 16 is called Superposition of Waves, Beats, and Standing Waves. This section has some kind of interesting illustrations in it that I'm able to show you via video, which I think will be good. When two or more waves pass through a medium, the net effect on the medium is a wave whose displacement at any point is found by adding the two or more separate wave displacements. So basically what we're saying is if you've got two sound sources in the same room, then depending on exactly how they're arranged, what the frequencies are, and where the observer is, you could actually get a sound that is more intense, that it's actually louder in some places, or potentially you could get the sound from those two sources interfering with one another in a destructive way so that the sound's actually quieter to the person in the room. So I have a Desmos example here that we can look at to kind of illustrate what we mean by this. But before we switch over there, let me just run over this quick stuff here, that when the waves are in phase, we say in phase if basically they're well, you'll see in the graph. I'll point out what in phase means. But we get constructive interference, which basically means that the appearance or the result is, the perception is that the wave is actually got a higher amplitude than either of the two original sources. And then if the waves are out of phase, then they kind of cancel each other out, and we get an amplitude that's much lower than either of the two original sources. And here we see two waves. All right. The amplitude for the green wave is 1. I can change that if I want to make it 2, 3, 4, whatever. For right now, we'll leave it at 1. The L is the wavelength, so I can move that in and out if I want to. I think it was at 5. I'll leave it there for now. And then the phi, this is the phase angle. So right now, these two waves are in phase. And by that, I mean that their peaks are lining up, their nodes are lining up, their troughs are lining up. Everything is exactly lined up. And if I move this slider, I can see that what I'm moving is actually the red wave. And so I can try to move them to the point where they are out of phase, which would be somewhere in there. So their nodes still match up, but now where the red curve has a peak, or the red wave, where it has a peak, the green wave has a valley or a trough. So we can see that they are now out of phase. Okay, so let me slide that back to 0. And then here is the, actually don't want that to also be green. I'm not sure why it's green. Let's make it blue so it stands out. All right, so now the blue wave represents the sum of the two waves. Okay, notice it says y3 equals y1 plus y2. So basically the blue curve, y3, is the sum of these two. So when the two curves are in phase, I get a much higher resulting amplitude. Whereas if I move them out of phase, notice that what's happening to the blue curve is that the amplitude is lower than the red curve. It actually matches the green curve. This is maybe more it illustrates it better if I make the amplitudes of these two waves the same. So let's make amplitude 1 and amplitude 2 both be the same. So now you almost can't see that there's two waves there because they're in phase. So I'll move them just slightly apart. So now the green and the red waves have the same amplitude. If I now move them to the 3.1-ish area, which you'll notice is pretty close to 3.14, we see that they're out of phase. The red and green curves are out of phase, and the blue curve is almost not a wave anymore, right? It has just a very tiny amplitude now. So this is caused because if I add the green wave and the red wave, then just about everywhere the two waves are opposites of each other. I have a positive value. If I have a positive value on the red, I'm getting a negative value on the green, and add those together, and you get pretty close to 0. If I could make this exactly 3.1415, yada yada, then that blue curve would actually become a line. All right, so notice that close to 0, or at 0, these two waves are perfectly lined up, and I get a higher amplitude than either of the two original waves. And as I start to move the phase, I can actually put it here so I end up with what ends up being 3, almost, there we go. Now 3 waves that are almost exactly the same. So notice that we're out of phase by 2.1 radians. So it gives us kind of an interesting picture where we get 3 waves. The blue wave is still the sum of the other two. And then as we get close to pi, we see that they almost disappear. And I can go to, if I get to 6.28, which I'm not able to get to exactly, but that's pretty close, I get, I'm back to having in phase waves and a much higher result. All right. Okay. So our next example comes from this idea, okay, difference in path length. If we have 2 sources, like in this picture you can see they're speakers, and they are producing the same wavelength, same frequency sound, then depending on where this observer is, point P represents the position of the observer, we may experience the sound coming from these 2 speakers in unexpected ways. So the difference in the phase angle can be found this way. Our delta phi is going to be equal to 2 pi over delta x divided by lambda, which remember lambda is our wavelength. So delta x I think is equivalent to d in this case. Delta x. Actually, no. I'm sorry. Delta x is the difference between x1 and x2. So x2 minus x1 gives us the delta x, so the change in the phase angle is there. So we're going to use that little piece of information to work out this example. This is basically exactly as that picture was on the 2 slides ago, only now we're told what the frequency is, 1720 hertz, and we want to try to figure out how far must speaker 1 be from speaker 2 in order to get destructive interference.
All right, so for example number 11, what we are trying to figure out is how far apart should these speakers be in order to create destructive interference at point P. Oops. So in order for that to happen, in order for destructive interference to happen, distance x1 from the first speaker to P and distance x2 from the second speaker to P, they need to be different by half a wavelength. Okay, so another way of saying that, what I'm trying to say, is that x2 minus x1 needs to equal 1/2 lambda. Or, since x1 is known, we know that's 20 meters, we can just solve for x2, say that it's going to be x1 plus 1/2 lambda. So, x1 is 20 meters. And our lambda is 20 centimeters, so half of that would be 10 centimeters or 0.1 meters. Oh, I got my decimal in the wrong place. 0.10 meters. So now that we have that, this just basically becomes a Pythagorean theorem problem. Okay, our distance is going to equal the square root of x2 squared minus x1 squared. So 20.10 meters squared minus 20.0 meters squared. Take the square root of all that, and we get, what do we get? We get 2.00 meters. So if the speakers are placed 2 meters apart, then at point P, the observer would actually hear no sound at all. If point P actually moved to being halfway in between, so if we could kind of draw a perpendicular line here and put point P in the middle, then the person at that point would experience an amplitude that's twice as great as either one of those speakers by themselves, because we'd get that constructive interference. All right, but this is the answer here for number 11. We were looking for destructive interference, and there's our solution.
All right, the next idea is one called Beats. And this is not expensive headphones. This is actually kind of an interesting idea that I thought about trying to illustrate with my guitar, but I don't think the sounds were really coming through on the speaker or on the microphone of my phone. So the idea is when you have 2 frequencies that are pretty close together but not quite the same, then you hear them, and you hear what almost sounds like a beat. Beat is not the word that I would have chosen if I had been picking this, but that's the way they describe it. And this picture here is supposed to kind of illustrate that. And if you're close to to having the right frequency, but not quite, then what can happen is, notice that here at this point, T1 and T2 are in phase. Okay, the peaks of those waves are the same. But then by the time we get to here, T1 is now at a trough and T2 is at a peak. And so in this area where they were in phase, you get a large amplitude. And then here where they're out of phase, you get that zero amplitude. So you get this sort of oscillating wah, wah, wah kind of effect. But anyway, this is the idea of the beat that we hear when two frequencies are close to each other, but not exactly the same. All right, moving on to standing waves in a string. This is I have an illustration here on using my guitar for these harmonics and the standing waves in strings. So if you read through this slide and then check out that video, hopefully all of this will make good sense. To calculate harmonic resonant frequencies for a string, we can find the first frequency by taking v, the speed of the wave, divided by 2 times the length of the string. Second harmonic is twice that. The nth harmonic is just n times that first harmonic. So for strings, we can always just multiply by the n of the harmonic that we're looking for, and multiply by the first harmonic, and that'll give us the frequency of the nth harmonic. So here's an example that we can work.
All right, for example number 12, we want to find the first, second, and third harmonics for a string that is 80 centimeters long with a wave speed of 400 meters per second. So we know that the first harmonic, also known as the fundamental frequency, that's a term that I think shows up in Albert a good bit, but it's not really mentioned in our book. So be aware of that idea. Fundamental frequency is also that first harmonic. Those two names are synonymous. So for this, our speed is 400 meters per second divided by 2 times the length, which is 0.8 meters. So 400 divided by 400 divided by 1.6 is 250 hertz. Oops, that's not, I missed half the number. 250 hertz. Then after that, each second harmonic, third harmonic, nth harmonic up above that will just be n times f1. So a second harmonic will be 2 times f1. So that would be 500 hertz. And then our 3 times the fundamental harmonic, or excuse me, fundamental frequency will be f3, which would be 750 hertz. So pretty simple calculations on this one. Nothing real difficult. You just need to make sure that you have straight when to use this formula and how it differs when you switch to an open or a closed pipe with a standing sound wave.
All right, standing sound waves is similar to the idea of standing waves in a string, but there's an important difference. Think of this as like the pipe from a pipe organ. I don't know if you guys are familiar with that, but basically the pipes are sized in such a way that they each have a specific resonance. So sounds that are introduced at one end are amplified by the time they get to the other end. I demonstrated this in class if you were there. I had a piece of PVC pipe that resonated C, and when I stuck the tuning fork just into the edge of the opening on one side, it amplified the sound. You could hear it much more clearly than if I just held the tuning fork outside of the pipe. And this is the idea of that. Okay, this is very similar to the guitar string idea. If you haven't watched the guitar video yet, go ahead and watch that real fast, because there's an interesting difference between the two. On a guitar, our nodes would be at the end, okay, and our amplitude, the highest point of the amplitude, the antinode, would be happening in the middle. But with a pipe, we actually get our antinodes at the end, so we have the largest amplitude at the ends of the pipe, and the node happens in the middle for the first harmonic. So our frequency is V over 2L again, but the wave is kind of backwards from the way it was on the guitar. Similarly, we can find the second harmonic by multiplying 2 times the first harmonic. 3 times the first harmonic will give us the third harmonic, etc., etc. So interesting, but different. So with a closed pipe, though, this is actually kind of a hybrid between the two, because at one end we have a node, the closed end, and at the open end we have an antinode. We have the largest amplitude. So interestingly, with this one, we're always going to end up with what looks like half a wave, or an unfinished wave at the end of each of these. So what that means is that we're never going to have an even harmonic from a closed pipe. So the V's for both the closed and the open pipe are typically going to be the speed of sound in air, which most of the time we're going to assume that the air is 20 degrees Celsius, so that'll be 344 meters per second. And then we divide by 4 times the length, and that'll give us our frequencies. So I think that's everything that I need to tell you for closed pipes. And so there's some fairly detailed information here in Chapter 16, and I've tried to focus in on the ones that show up in the WebAssign. If I missed anything and you guys have questions, certainly I want to help answer those. But I think I've covered all the major things that you're going to need in order to do that. So good luck on this. I will talk to you soon.